Hello, everybody. This Screencastify is going to be dealing with the beginning of our chemistry unit and talking about the particles that make up everything. Those particles are called atoms, and we're going to be discussing atoms quite a bit in the next few lessons. But before we get into that, we need to really talk about how those particles, how those atoms move about. Okay, and so that's what we're going to be focusing on in this lesson, which you can see from the screen here is particles in motion. Um, so, starting off, basically, all matter is made up of small particles that are constantly moving. So, it doesn't matter if you're talking about this pen, if you're talking about the ink inside of the pen. Get this out. The ink being a liquid, the pen being a solid. It doesn't matter if you're talking about the gas that I'm breathing as I talk. All matter, all things, whether you're talking about living or non living, are made up of small pieces that are constantly moving. And so that's what we're going to be focusing on in this video. Um, Now, those particles move about, as it says, they're in random motion in all directions at different speeds. Okay, how they move really depends on a couple different scenarios, a couple different facts. One of those two facts, which we'll talk about in a minute here, is if there's being heat added to it or not, or heat removed from it. Another is what type of object you're talking about. Is it a solid, a liquid, or gas? That also affects how those particles move. There can be other factors as well, but those are the two main ones that we're going to be focusing on. And the random motion allows for what's called diffusion, or movement from areas of high concentration to areas of low concentration. Um, I like to think about this with if you spray perfume or you spray cologne. Um, if you spray it on you, the people directly around you will smell it rather quickly, depending on how much you spray. But after you spray it, people a table away might be able to smell it 30 seconds later, depending again how much you spray. It might eventually work its way across the entire room. It also works with air fresheners. If anybody's ever, made a smell that wasn't too good and you spray an air freshener, that air freshener eventually will move across the room so that everyone can smell it. Now, the people right close to it where it was sprayed will smell the greater amount of it, the further away, less. Well, the reason that that happens is what's called diffusion. And you can see here in these particles, the particles are all concentrated highly together, but they don't like that. The particles want space to move. And so what they do is they start to move apart from each other to have their own area, okay? They want their personal space. And so that is called diffusion. They move from an area of high concentration, or a lot of them, to an area of low concentration, or only a few of them, okay? Um, Next, as I said, one of the things that can affect how those particles move, how fast they move, or if they move at all, or not if they move at all, but how fast and how slow they move, is how much heat is either being added to them or taken away. Um, and that is through gaining what is called kinetic energy. Okay, kinetic energy is the energy of motion. The more motion, the more energy. Okay, so the more something is moving, the more potential energy, or the more actual energy, kinetic energy it has. Okay, and we're going to talk about potential energy here in a little bit as well. How that is measured is and what's called a joule. A joule is the label for kinetic energy. So if something has kinetic energy that equals 34, for example, it would be 34 joules. Okay, that's how much energy it is. So, just like you can, when you weigh something, it's in grams, and when you're measuring kinetic energy, it's in joules. Okay. Thermodynamics is the study of this process of how much heat is either being added to or released from objects, and how much it has there in it already. And the guy that came up with this, that's given the credit for this, is a guy called James Prescott Joule. He was an English physicist, and of course, the name Joule came after him. One other thing we're going to be talking about and learning about is one of the math parts of science, which I know a lot of you don't exactly love. But kinetic energy does have a mathematical way to explain it, and it has a formula that you do need to be aware of and know how to use and how to do. This right here is the formula. It's kinetic energy equals 0.5 times mass times volume squared. You can also think of this as half, but I know a lot of you don't like to deal with fractions, so I just dealt with it as a decimal, okay? So basically, if you've got, in this, Ke equals kinetic energy, m equals mass, and v is velocity. And velocity, another way to say that is speed, how fast something is going. So if I want to know the kinetic energy of something that is 150 kilograms, and it's going 15 meters per second, okay? Remember, the M here is going to be meters. It's not miles because we're dealing more with metric than with standard. And plus, if it's miles, it would be MI, okay? So it's 15 meters per second is how fast it's going, and it weighs mass is 150 kilograms for the object. So all you do is you take 0.5 times the mass, which is 150, times the volume squared. So we're going to square 15. And remember, to square something means times itself. Okay, so this is what it would look like right here. This is actually three-step problem. The first step you do is we have to simplify the 15 squared. So the 15 squared simplified is 225. So 15 times 15 basically is 225. Then when you take 225 times 150, that is your second step, and that equals 33,750. Add that comma in there. Then for your last step, you're going to take that times that half or times that 0.5. And so the kinetic energy, how much energy that object has going at 15 meters per second, is 16,875 J for joules. Okay, so that is the formula that you do need to be aware of and be able to use to be able to solve these. Okay, so that is the first set of our notes for particles in motion. With that, your assignment is, here it is this assignment right here, particles in motion exit ticket. And you're going to answer these on the page. All of these should be able to be answered from the notes that we went over. However, there is one here, number 8. So it says, hot air balloons typically fly in the early morning or late afternoon. Briefly explain why and discuss the air particles in the balloon and outside the balloon. There is an ed puzzle that is also going to be assigned to you that will help to explain why the hot air balloons work the way they do. Okay, so that's one of the 2 assignments with this. The other is going to go along with our second set of notes here, and you can kind of use both sets of notes for both assignments. Since this is kind of a big topic, I broke it up into 2 sets of notes. So the second set of notes is particles in motion, part 2 here, and it's still continuing with the idea of how much energy something is going to have depends on how much heat is added or being taken away. So with that, if you remember from the last set of notes, we talked about thermodynamics. Okay, therm means heat. So thermodynamics is the study of all of this. So thermal expansion basically means to expand because of heat. Okay, and thermal contraction means the heat causes it contract, means come in. Okay, so thermal expansion, something expands because it's heated. Thermal contraction, if it expands because it's heated, then contraction is going to be because it's losing heat. Okay, so the increase of material volume when particle motion increases or when particles decrease. So they're going to decrease. The particles are going to move slower when they lose energy. Okay, so when it's colder, they're going to move much slower. So they're taking away the heat. So thermal expansion, you're adding heat. It's going to move faster. The particles will move faster. Because they're moving faster, they're bumping into each other. They make it expand. Okay, we're going to see this for just a second here, but it's typically in bridges. Okay, well, and in concrete and a lot of different stuff. But the main example we're going to be working with is in bridges. If you ever look at a bridge, especially any kind of steel bridges, they don't fully connect at the end. There's going to be a metal grate at the end. And the reason for that is that when that bridge gets really hot during the summer months or whatever, it needs to have room to expand, because if it was joined up right away, when it heats up, it would crack and it would break that ending and fail. So thermal expansion basically helps to explain how we have to leave that space there in that bridges so that they don't crack and don't fail. Because if there's no room in between them, then it wouldn't have anywhere to expand. So when the bridge expands, you still have enough room, it still works. If they were side by side and the bridge tried to expand, it would push on each other, crack. Thermal contraction is how it kind of the same idea in the wintertime. You've got to have a little bit of space so that if it was side by side like this and it contracted, that means it's going to try and pull away from here, and so there's nothing connecting it, and again it would fail. Okay, so you've got to have this kind of, it's usually a zigzag pattern, but you've got to have that space so that it can metal typically, but it can happen in a lot of different substances. It has that room to expand or to contract, okay, to either get bigger or smaller. So thermal expansion and contraction can be used to measure temperature. The measure of the average kinetic energy of the particles in motion is temperature. Okay, so how much average do they move about? You know that temperature in the United States, typically we use Fahrenheit. That is called the standard form of measurement. However, pretty much most of the rest of the world uses Celsius. The C here. That deals with like the metric side of everything. And in science, we typically use Celsius more than Fahrenheit. There's one other way to measure temperature, and that is Kelvin with a capital K. And basically, we use that one when we're talking about extremes, okay? Extreme high, extreme low temperatures, okay? And so Kelvin is really only used typically in science, okay? And when we're dealing with like lab results and stuff like that. Okay. Next slide. Particles in gas behave different from liquids. So if you remember at the beginning of this video, I talked about how there was two big things we're going to talk about that affects how much the particles move, those atoms move. And I said it was the heat being added or taken away. And the second way was whether it's a solid, liquid, or gas. Okay, so this picture here kind of helps to explain it. The next slide will explain it even more. But particles in gas, for example, behave much differently than liquids and solids. These particles, if there's, say oxygen is trapped inside of this container because you got the plug right there, so it's trapped inside of here. As those particles move about, they have only so much space to move in, because you can see they keep bouncing off the sides here. They're going to bounce off of each other. And so because of that, they're going to behave differently because they have that different type of space to move in. And an odor. Okay, sorry about that interruption there. So as I was saying, that the particles move differently. We talked about this a little bit, that the odor can be detected further away. We talked about that with diffusion, how, as it moves away, it can be detected further away. And that gas particles basically will continue to move apart until they run into something. So if this lid had not been on here, these would be moving out of it. They're going to move until they can't. And gas particles have a high amount of energy because of that, okay? And lastly on this, to kind of show you how those particles move, we saw the gas particles here, how they're kind of moving about and how they'll kind of just bump into the sides. And if there's no lid here, they're going to move out of that as well, and other particles will move in. And so it's constantly moving, a lot of high energy here. Liquid, you can see, they're more concentrated down here at the bottom. Now, they're not as tight as the solid ones because of them being liquid. They're going to take up basically the space of whatever container they're in. Okay, if this container was a lot thinner, then they would take that spot. It's basically whatever they're on. If this was spilled out on the table, then it'll take on the shape of the table. They will go with whatever container they're in. Whereas the gas, it just keeps going until it can't anymore. And solids, they basically have more of a stringent or a more solid, more of a set pattern. They will keep that exact same shape until it's changed by adding heat or adding pressure, or usually heat, but you're going to have to change it in some way in order for that solid to be changed. Okay. So if you look at how much energy each of these has, gas, great amount of kinetic energy, a huge amount of kinetic energy. Liquid, kind of, a little bit. And then finally, solid has very little. Okay. The particles are still moving. These particles, even though they don't look like they're moving, they're vibrating, but they're vibrating, next to each other and bam, 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 hitting each other. So they are moving, but they're not moving as much as these two. Okay. So low, medium, high amount of energy. Okay. All right. And your other assignment with this is your web quest here. There are a few pages to it, so make sure you do each of them. Go down here. This one here, I want to explain real quick. This is to show how roller coasters can show you both potential and kinetic energy. If you remember, I told you a little bit about kinetic. Well, this web quest will introduce you to potential energy as well. And if you click on that website, hopefully it's working. You'll be able to see a roller coaster and how, depending on where it's at in the roller coaster, how much potential energy it has, how much kinetic energy it has. Okay. All right. So here it is. Here's the roller coaster. Okay. So as I was saying, you can see here the difference between potential energy and kinetic energy depending on where you are on the roller coaster. So if you click launch, and it comes up here. All right. And so what you're going to want to do is you want to go hit the step button here, not the play, okay? Because play will go all the way through it. We want the step button. So if you click step, it's going to show you the roller coaster going up to the peak of the first hill. And when that happens, how much potential energy is compared to kinetic. So on your assignment here, you would just need to tell me, is there more kinetic or more potential? So you would just simply put in kinetic or potential, whichever one there's the greatest of, which you can see from right here, the greatest is potential. Okay, that means there's a whole lot of energy waiting to happen, but nothing yet, no movement. So I would just put potential right there because that's step one. Then I would hit continue. Okay, and step two, you can see the majority of it is blue, so that means the majority of kinetic energy. And so you continue on like that, okay, all through all the steps. So that's all of that right there. You'll just tell me which one. Is it the blue that's the greatest, which would be kinetic energy, or is it the pink that is greatest? I think that's right. Did I do the right colors? Yes. Or is it the pink that is greatest, which would be potential energy, okay? And then last but not least, this one right here is just a quiz game, like kind of a matching thing. Just you want to complete it and then put down what your score is right there. Okay, so pretty simple other than that. And this is the website right here that you're going to use to answer these questions. Okay. All right, so if you have any questions, let me know. So basically, with this particular assignment, you will be given the two sets of notes we went over. You'll be given the two assignments and then the ed puzzle. Okay, so make sure that you complete all of those, and I'll have the due date on the classroom assignment. Okay. All right, let me know if you have any questions, and good luck.